that web quest, what was the definition of work? Yeah, Hassan. Yes. So work is the transfer of energy from one object to another. The transfer of energy from one object to another. And I do want to point out that it doesn't need to stay as the same kind of energy. When work is done, typically it actually takes one kind of energy and turns it into another. So frequently turns one kind of energy into another. Turns one kind of energy into another. All right. Also from that web quest, how do we calculate work? Come on, Logan, don't let me down on this one. How do you calculate work? Taylor beat you to it. Work is MAD, which is the breakdown of it. We could write step forward from that is work is force times displacement, or work is MAD. Mass, acceleration, displacement, because force is mass times acceleration. So this is force, and this is displacement. In order for work to be done, a force applied to an object must cause it to move in the same direction. So if you've got a force being applied to an object, but it's moving the other direction, the force isn't doing work. If you've got a force being applied to an object and it's moving perpendicular to the direction you're pushing, you're not doing work. So work is only done if the force pushes the object in the same direction the force is acting. The object in the same direction the force is acting. Meaning it actually has to move in that direction. So if I take this textbook here and I hold it here, am I doing any work? Why no?
Yes, you are.
There's no displacement. It's not moving. Because there's no displacement, it's not moving. I'm not doing any work. Okay? How about now? Am I doing work? Yeah. I applied a force. I moved the book up. Now I am not. Only when I was moving it was I. Okay, how about now? Am I doing work? Why no? Just no. Okay. I did say that. There we go. So which direction am I applying a force as this book moves down? Which direction am I applying a force? Up. Which way is the book moving? Down. So I'm not doing the work. Gravity is doing the work. Okay? So one thing I want to point out is the difference that First Hour got tripped up on was the difference between doing work and applying a force. Am I applying a force? Yes. Am I applying a force as I lift it? Yes. Am I applying a force as I lower it? Yes. But only one of those am I taking my energy and transferring it to the book. The only one where I'm taking my energy and transferring it to the book is the one where I lift the book up. If I would go down and sideways, there's a little small amount of work being done when I start moving it sideways. But because an object in motion stays in motion, I'm only really doing work as I accelerated that initial motion. This whole path, no, I didn't do any work. This little bit where I got it to go to speed, yes, I did work. So that's a trickier one. For the most part, no, I wasn't doing any work. Like right now, am I doing work to the book? I'm not doing work to the book because we're moving at a constant speed. I'm not applying any force horizontally to it. I'm applying a force up. So that was a little trickier. So if I just carry it, no, I don't do any work after I've started moving. That one is a little tricky. All right. And I did mention up here that it can turn one kind of energy into another. And I want to show a situation where we're talking about non-mechanical energy. All right. So work changes one type of energy into another. Demonstrate that pretty clearly. Yes? All right. The other topic we've got to talk here real quick is power. From the simulation that we did on Tuesday, what's power? Shh, say again. The ability to do work, that's definitely part of it. Anybody got the rest? Yeah. All right, I'm going to come back to you then, Aiden. That's the equation that I just said I was going to come back to her for. All right, anybody else? So the ability to do work is a reasonable start to it, but it's the rate at which you do work that gives us power. So the rate at which work is done. Say again. I'm not sure the context of that statement. If you have something that's using power, then work is done. Oh, okay. All right, so power, the rate at which work is done. And as Lauren and Aiden were giving me the equation, power is work over time. Okay? Where work is measured in joules, because it is moving energy around, and time is measured in seconds, we could label power as joules per second. However, we don't. We have a special unit. What's the special unit? Watts. When we talk about, say, the power of just you lifting a book up, or the power of gravity causing something to fall, this is the same power that lights a light bulb. Okay? Power in each case is a measure of how much energy per second is being used. Doesn't matter if we're talking electrical or mechanical, it's all the same. Okay? Let me see here. I need a new page. All right, so I'm going to take us back to notes from Monday. All right, we had point A, we had point B, we had a roller coaster on there with a couple of people inside of it, and we've determined that it doesn't matter how big these people are because they'll be going the same speed at point B regardless, correct? Okay. We also said that if that was above the ground a little bit, what kind of energy did we have at point A mostly? Gravitational potential, GPE. At point B, what kind of energy did we have? Kinetic energy. Could we have gravitational potential energy there? Yes, if what? If you're still above the ground. I mean, what if we are still above the ground? Do we still have to consider there to be gravitational potential energy there? Do we always? No, we don't always. Why not? Yeah, because we're not going to fall any further. If this is the lowest point we're going to talk about in this problem, then call that zero. Remember we had the discussion with the, wherever band ball went, about dropping it and saying the table is zero versus saying the floor is zero versus getting a jackhammer in here, drilling a hole into the floor and saying, oh, the pit that I just made, the bottom of that is zero. Well, we could just keep going and going. So just call zero whatever's the most convenient thing. If we're not going any lower than the bottom of point B, call that zero. Make sense? Okay. So we know that kinetic energy here comes from where? Yes, gravitational potential energy here. Where does that gravitational potential energy come from? How does a roller coaster get to the top of the first hill? Yeah, there's a chain system that pulls it up. So there's some kind of motor down here and a chain that runs all the way up to here. So the chain and the motor here are doing work. They're applying a force to the roller coaster car. They move it to displacement, and as they move it up to this point, they have done work, and that work turns into gravitational potential energy. Now that work is changing maybe electrical potential energy into gravitational potential, because maybe this is an electric motor, maybe it's a diesel motor, so maybe we're changing chemical potential energy into gravitational potential. Doesn't matter what kind of motor this is, where the motor is getting its power, work is what turns it into gravitational potential energy. Okay? So let's see here. If we talk about the different types of motors we put here, the different types of motors we could attach here could take us to the top of the hill at different speeds. They could get us there in different amounts of time. So a higher powered one would get us up there faster. A lower powered one would take a little longer, but we'd still get to the top of the roller coaster. That's the only difference that we would experience. They still both get us there. They still both do the same amount of work, but the one with more power gets us to the top of the hill faster. So sources with different amounts of power. Oh, okay, we're going outside.